some kind of an issue with the file. The file that I've been writing on has been getting too big. So this is actually pretty much a fresh version. So there's going to be a split in the manuals, if you know what I mean. There'll be two of them now. Yeah, so okay, let's get going. So more partial fractions. So let us think back. What are we doing? We're trying to write these. Partial fraction expansion is when you got a rational function that's a polynomial divided by a polynomial, and here we've got a, say this is a degree 2 polynomial divided by a degree 3 polynomial. The degree is the highest power, so the highest power on top is squared, and if you multiply out the bottom, the highest power is cubed. You want to send this back using the inverse Laplace transform, but if you look in the tables, there isn't anything as complicated as this. So what you have to do is write this as a sum of simple terms. So that's what we need to do here. We need to write this as a sum of simple terms. Okay, so the first step is, in this you need to factorize the bottom. Now 4s plus 1 is done, but what about s squared plus 1? Can we factorize this further? So there's a comment there, it can be factorized over complex numbers, but we won't be going there. So I'm going to give you some reasons why you can't factorize it, and they're all going to boil down to this factor theorem, which we probably mentioned before, but now we're really going to mention it. So if p of s is a polynomial, so the thing on top and the thing on bottom here are both polynomials, just sums of powers of s. K is a root if and only if s minus k is a factor. Now, what does it mean to say k is a root? It's a number that you input into the polynomial and you get out 0. Okay, so this double arrow means it works both sides, and I think the theorem that we're mostly going to actually use is what you'd call a corollary of this. So it's just something that follows. No real roots no real factors. Now, what I won't specify exactly. Well, what I mean by a real factor is s minus a real number. So if there's, because all the factors come from roots, so if there's no real roots, there's no real factors. So if the roots are all complex, then there's no real factors. Now you can have real factors with s squared, but not just s. Okay, so so a lot of this is kind of explained. The pk equal to 0 is explained there. Right, let's go. So so we're using this theorem. We've no real roots implies no real factors, and I'm going to be saying that multiple times over the next few weeks. No real roots, no real factors. Okay, so I have a number of explanations here for saying why you can't factorize s squared plus 1 any further. So because s squared is positive, now that's if you're considering s to be a real number, it's positive, its square is positive. So s squared plus 1 is definitely bigger than 1, which is strictly bigger than 0. So s squared plus 1 is strictly bigger than 0 for real numbers, and that means it's never equal to 0. So there's no real roots, no real factors. So that's one example. Another one is if you look at the graph of y equal to s squared plus 1. Now what we might plot first is y equal to s squared, which looks something like this. And that does have a root. But if you do s squared plus 1, it's the same graph but shifted up by 1. And if you look at this one, like remember all the points on the graph of a function are of the form input, output. So they're all of the form s. In this case, the output is s squared plus 1. And there's no point on that graph, the top one, where the y coordinate is equal to 0. So that means s squared plus 1 is never equal to 0. So that means there's no real roots, no real factors. If you try and find the roots directly, you try and solve s squared plus 1 equal to 0, you get s squared is minus 1, but there's no real number squared equal to minus 1, so no real roots, so no real factors. You could also look at the minus b formula. You end up with square root of a negative number, because the thing inside the square root, the b squared minus 4ac, is minus 4, which is negative, and so no real roots, no real factors. And generalizing, s squared plus an omega squared has no real factors, but totally different scenario if we have s squared minus omega squared. That does have factors because it's s minus omega times s plus omega, and none of the arguments above apply to s squared minus omega squared. So for example, if you try and solve s squared minus omega squared equal to 0, you get s squared equal to omega squared. Take square roots and be careful, you have s is plus or minus omega. The graph of s squared minus omega does actually cut the x-axis. So if you start with s squared and then do negative, you'll come down here. So this would be y equal to s squared minus omega squared, and the roots would be, that'd be omega, assuming omega is positive, and minus omega. So s squared minus omega squared has two roots, so it has two factors, s minus omega and s plus omega. Okay, so let's be careful what I'm writing above here. Now I've left no room, unfortunately, on this next page, so I'm going to have to write little tiny writing. So what did we have originally? 6s squared. So basically the bottom can't be factorized anymore. 6s squared minus 3s plus 1 divided by, I think it was 4s plus 1 times s squared plus 1. So you can't factorize any further. You look at the rules now. So this is a rule 1, but this is a quadratic and s squared that can't be factorized anymore. It's a rule 3. So this, now I'm going to have to do an equals dot 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 here. So rule 1 says it'll be some constant divided by 4s plus 1. And rule 2 is going to say it's some constant times s plus a constant divided by s squared plus 1. So that's what rule 1 and rule 3 actually say. Now, the story now is that I haven't really got space. I'd like to write this as a single fraction. I don't have the space. I'm going to go dot dot dot. This will be equal to 4s plus 1 times s squared plus 1. So if you multiply the first term, the a over 4s plus 1, above and below by s squared plus 1, you'll get the bottom will be 4s plus 1, the bottom will be s squared plus 1, the top will be as squared plus 1. And similarly, if you multiply the second term above and below by 4s plus 1, you'll have another common denominator. So that's a little exercise for you. Usually when I have space, I will do it, but I just don't have space here, I'm afraid. So we're trying to, let's look back at what we're trying to achieve here. We want that to equal that. And the thing with the red is equal to the thing at the end. So I want the thing on the left to equal the thing on the right. Now what we notice is that the bottoms are equal. So that's good. They're equal. So if we want these to be equal, what we need is the tops to be equal. Okay. So if I can force the top of the right equal to the top of the left, then I found my ABC. Okay. So that's written on the next page, yeah. So we want these to be equal. So there's different ways of doing this. You can multiply out and compare coefficients. So for example, if you look at the coefficient of s squared, it should be a plus b. So you have a plus b is equal to 6. And you can do that with s, and you can do that with the constant. But what I'm going to do is I'm going to substitute in values of s. So what's the clever value of s to substitute in? Well, probably the cleverest thing to do would be to kill this thing. Make this equal to 0. So I want to pick a value of s that 4s plus 1 is equal to 0. Now, some of us can do that in our head. It's minus a quarter, but if you can't, take away 1 from both sides. Divide both sides by 4. S is equal to minus a quarter. So I'm going to put s equal to minus a quarter into both sides. So I'm going to get 6 by minus a quarter squared minus 3 times minus a quarter plus 1 equal to a, which I'm looking for, minus a quarter, you need brackets with that sign, plus 1. And the second bit you don't really need, because if you put s equal to minus a quarter into the 4s plus 1, you're just getting out 0. So it'll be just b times minus a quarter plus c times 0, so that's just equal to 0. So we can just forget about that. And that's why we chose a minus a quarter. Now what I'm going to do is I'm going to bang into the calculator the stuff on the left hand side. I'll probably just pause. No, I won't pause. So it'll be 6 by, ends up being 1 over 16 plus 3/4 plus 1 is what it ends up being, 17/8 equal to, and that other thing looks to me like possibly 17/16 times a. Now you can mess around here and be smart, and you can multiply both sides by 16, but to be honest, the easiest thing to do is a is multiplied by 17/16, so just divide both sides by 17/16 and you will be done. It's a bit messy, but sure, that's what a calculator is good at. A equal to 2. Okay, now what else can we kill? Now unfortunately you can't kill that, and that's why we couldn't factorize it. You could, if you were very smart, put in plus and minus I, but I don't really recommend that, to be honest with you. So what's another clever value to put in? Now really what you should just put in is something simple now, and the simplest thing you can put in is 0, and what's good about that is that will actually kill the b, and we'll have an equation in a. So the next thing to put in is s equal to 0. So 6 times 0 squared is just 0, minus 3 times 0 is just 0, so on the left we just have 1, equal to a times 0 squared is 0, plus 1, equal to, not equal to, b, plus b times 0 is 0, plus c, 4 times 0 is 0, plus 1 is 1. So we end up with, and of course the thing is, we know what a is equal to. We've just found that a is equal to 2. So I end up with writing on the left hand side, 0 plus c by 1 is c, plus 2 is equal to 1. So we take away the 2 from both sides and we get c is equal to minus 1. So we got 2 of them. Now what are we left with? We're left to find c or b. So we'll just put in the next easiest number that you can think of, say s equal to 1. So you get 6 by 1 squared is 6, minus 3 by 1 is 3, plus 1, equal to a, which we know is equal to 2. 1 squared is 1, plus 1, plus b times 1 is b, plus c we've already found is minus 1. 4 times 1 is 4, plus 1. So we'll tidy this up a little bit. I'm going to work on the right hand side. So I have 5 times b minus 1, plus 2 by 2 is 4. 6 minus 3 is plus 4. I think we'll get. Now I think you're going to have to get b is equal to 1 here if you kind of think. It's funny, there's clever and stupider ways of doing this. So everyone really, to be honest, a third year engineer should be able to solve this. There's no two ways about it. So I'll just show you kind of a cleverer way. You can take away the 4 from both sides. And then you've got two numbers multiplied together giving you 0. The only way that can happen is if one of them is 0. 5 is not equal to 0, so you have to have that b minus 1 is equal to 0. Alternatively, divide both sides by 5, and so we get b is equal to 1. And loads of space here. So if a is equal to 2, c is equal to minus 1, and b is equal to 1. So now we go back to the bit in red and put in the a, the b, and the c. So what actually happens now, so that's the a was 2, that's the a over the 4s plus 1, the b is 1, so it's 1s, and the c is minus 1, so you get here. So later on, so you've written as some of simpler terms. What we're going to do is you need to manipulate the first term a little bit. I'm a bit confused myself now over what I've done. Yeah, so there's a bit of messing around here with this. So what you actually do with this is, I probably have space to look at this now. So you're looking at this and you go into the tables and all you see is 1 over s plus a, and this is not of the correct form. So what you want to do is you want to get rid of that 4 on the bottom. So what you'll do with this is you'll divide above and below by 4, which is the same as multiplying above and below by a quarter. And a quarter divided by a quarter is equal to 1, so that doesn't change anything. So that's a legitimate thing to do. 2 by a quarter is a half. And then a quarter by 4s is s, a quarter by 1 is a quarter. And then what you can do is, I think we've seen this already, that like say if you have 2/3, listen to what we just said, 2 by 1 over 3. And you can do a similar story here. A half over s plus a quarter is a half times 1 over s plus a quarter. Okay, so that's that manipulation, that's the first one. And then the other thing is, say the s minus 1 divided by that, you can split that. So like if you look at, say, 10 minus 2 over 7, isn't that the same as 10 over 7 minus 2 over 7? Isn't that the same thing? So 10 minus 2 over 7, so that's 8 sevenths, is the same as 10 sevenths minus 2 sevenths. They're exactly the same thing. There's other ways of kind of explaining that. So one way I would like is 10 minus 2 over 7, that dividing by 7 is actually multiplying by 1/7. So these are little nicky-nacky algebra things. And then you can multiply in the 7. So you have 1/7 by 10 minus 1/7 by 2. And then we call 1/7 by 10 10 sevenths. And we call 1/7 by 2 2 sevenths. So this is how you this is what's happening here with the s minus 1 divided by s squared plus 1, splitting it up like that into s over s squared plus 1 minus 1 over s squared plus 1. And then if you go into the tables, you can do this should be the inverse Laplace transform actually. You fix the half, and then 1 over s plus a, you'll see in the tables, the inverse Laplace transform sends that to e to the minus at. And then the other ones you'll see that are relevant are s over s squared plus omega squared. Go back to cos omega t, and omega over s squared plus omega squared. This is all in your Laplace tables. You might want to print them out, by the way. It goes back to sine omega t. And so what you have here is the s over s squared plus 1 squared goes back to plus cos t, and this goes back to minus sine t. Okay, now there's a worked example given there that you can have a look at if you want. I'm happy enough for it. Right, now one of the things that we'll see is that you might be wondering, is there some kind of shortcut here? And in one situation there is a shortcut, and it's called the cover-up method, and it's fantastic, and you should use it if you can, whenever you can. Now you can't always use it. So if it's all rule 1s, you can do it. Now that means there's no repeated, so you can't have, say, s plus 1 by s plus 1, because that would be rule 2, or you couldn't have s squared plus 1, because that would be rule 3, all rule 1s. Like this one. It's probably easier to just show you how it works rather than describing it, and you're just going to take my word that it actually works. So you know from your partial fractions theory that there's going to be some constant over s plus 1 plus some constant over s plus 6. And I'm just going to write for a moment what these are, or a and b. I'm going to scribble them out, so don't write them down. So we know this. What the cover-up method does is it allows you to basically find them in one line. Now, I remember it only works for rule 1. So what you do, and unfortunately I can't, okay, maybe I can. So what we're going to do to get the, yeah, it's kind of easier to describe this actually in class. So to get the s plus 1, what we're going to throw in is we're going to be throwing in the value of s that makes that 0, which is minus 1. Okay, and to this one, we're going to sub in the value into something that makes s plus 6 0, which is s equal to minus 6. And why is it called the cover-up method? So for s plus 1, and this thing will also be scribbled out, you cover up the s plus 1, okay? And then you sub in the s equal to minus 1 into everything that's left. The 5s plus 10 and the s plus 6. Okay, so we'll do that now. So we've covered up s plus 1, and we're looking at 5s plus 10 over s plus 6. So that's everything with the s plus 1 is covered up. For the other one then, well, you cover up the s plus 6, and you're left with 5s plus 10 over s plus 1, and you're going to substitute s equal to minus 6 into that. So cover up the s plus 6, and you get 5 times s plus 10 over s plus 1. And as we said, you sub in then minus 1. Once you get it, it might seem complicated at the start, but eventually you'll get it, and you'll be delighted to have it, and it's handy. So for the s plus 1, you cover up the s plus 1. So that's the 5s plus 10 and the s plus 6. So that's on top of the s plus 1, and you substitute in the value of s that makes s plus 1 0. That's s equal to minus 1. And then for the other one, you cover up s plus 6, you're left with 5s plus 10 over s plus 1, and you substitute in the value of s that makes what's left, what makes s plus 6 equal to 0, which is minus 6. And then hopefully we can, well then not hopefully, definitely you're done, because it's just a calculator job from there. So I think the first one is a 10 minus 5, which is 5 over 5 is 1 over s plus 1. And the other one looks like 10 minus 30 is minus 20 over minus 5, which is 4 s plus 6. So much easier, but unfortunately only works when everything is a rule 1. Okay. So yeah, so that's kind of putting it into words. Yeah, okay, so let's do an example here. Use the cover up method. So we know that this is equal to some constant over s plus 8. Not be that big. Some constant over s plus 8 plus some constant over s plus 6. And we're going to be substituting into this one the value of s that makes the bottom 0, that's minus 8. And in this one, the value of s that makes the bottom 0, which is minus 6. Okay. So now we're going to do our cover up method. So first cover up s plus 8. And I think I can be a bit cleverer than I was about this. So what's left? 3 minus 8s over s plus 6. Okay. And then for the other one, cover up s plus 6. What are you left with? 3 minus 8s over s plus 8. And now put in the values that we spoke about. Minus 8, minus 8, minus 6, minus 6. And we can go into the calculator maybe to get these. So 3 plus 64 divided by, God, I made a donkey of that. 3 plus 64 divided by minus 2, minus 67 over 2. And then the other one, 3 plus 8 by 6 is 48, I think, divided by 2, 51 over 2. I think I just want to show that the numbers don't have to be nicer. Yeah, there you go. So that's the rest of your partial fractions. We'll be seeing loads of them. You'll want to be very good at definitely the cover up method and the rest of it, I suppose. Okay, so yeah, there's a little trick here. I may have mentioned this previously. You can look at it. I won't be using this trick, but you might see it yourself here or there. It's a nice little trick. It makes rule 2 a little bit easier. Okay, so that's everything on partial fractions.